All right, just so you know, I'm recording this.
Okay. Can we do like number 3?
Yes, we can. Let me get my whiteboard set up. Number 3. So we're starting to talk about a little bit of calculus. Okay, and we're going to go from slope into talking about what's called instantaneous velocity. So I'm going to kind of maybe expand a little more on this just to kind of teach some of the material there. So, all right, so we have S of t equals 3t minus 5. And we want to find the instantaneous rate of change at x equals 4. I think that's right. Okay, now, instantaneous rate of change is a little bit different than slope. For example, this is what this line looks like, right? Something like this.
Mm-hmm.
All right. Now, this is a little bit different because it's a line, and it actually makes it a little easier that it's a line. But generally, when we talk about instantaneous rate of change, we talk about the rate of change at any point. Now, realistically, for a line, the slope or the rate of change is constant. In this case, it's always going to be 3. Well, this one's pretty easy in that sense. Now, we also want to be able to use the formula for instantaneous rate of change also. All right, which I think looks like this. Let me make sure I use the right one here. And eventually we're going to call that a derivative. Okay, we're going to call that a derivative. All right, so let's just talk about the derivative of this at t equals 4. So I'm going to be using the formula from page 740. And then there's different formulas we can use. Okay, so we're trying to find really what's called f prime of 4 in that problem. This notation means we're finding the derivative at 4, which represents the instantaneous rate of change of this function at 4. And once again, we're going to come up with 3 because it's a line. But we'll look at another one that's not a line that maybe requires more thinking and more work here. So it says it's the limit as x approaches 4, okay, of, it's going to say f of x minus f of 4, oops, all over x minus 4. Okay, so I'm using that green box in the middle of page 740.
Yep.
Right? So then we're going to have to use that. And realistically, just to expand on this, this is nothing more than really what we'd have for our slope formula. Like y2 minus y1 over x2 minus x1. But obviously, yep, we only have 1 point, okay? So that's going to be the limit as x approaches 4 of 3x, and I could use t here, it doesn't matter, don't be confused by the change of variable, it doesn't matter at all, minus 5, subtract, then I got to find f of 4, or in our case it's s of 4, I think that would be 7, that seem right?
Yep.
All over x minus 4. Right, now this is as x approaches 4. Now, we can't really evaluate this limit because if we tried to evaluate it by plugging in 4 for x, we'd have a problem here. All right, so what we're going to have to do is we're going to have to do some algebra. So I think if I simplify this, it works out to look like so. Limit as x approaches 4 of 3x minus 12 over x minus 4, which if I do a little algebra, I think it turns out to look like that. Does that make sense?
Yeah.
And then what happens if I do this?
That's a 3.
That's our 3.
Yep.
So whenever we're dealing with a line, right? Whenever we're dealing with a line, the derivative or the instantaneous rate of change will be the slope.
Okay.
Okay. So let's look at one that's not a line. Let's look at another one here. And I might use a different formula, but it's really the same thing. Let's look at I'm going to go with number 4. No, well, I'll go with number 5 right now. It's a little more abstract. I'm looking for another one. Because there's all kinds of different ways we can use that formula there. So let's go with number 4 first. And I know that's not one that's assigned, but I think it can help.
I think it was assigned.
What's that?
I think 1 through 16 is assigned.
Yeah, I know. Oh, was it? Okay. Yeah, I have it written here. I thought it was multiples of 3. So, sorry. I have it written down. I just didn't see it. So, number 4. Same thing, S of t, but it's a different type of function. What's going to be different is the algebra it takes to evaluate the limit at t equals 2. Right, and this one's a little bit different because this is what this graph looks like, and you can graph it on your calculator if you want to. Take a look, something like this. Okay, that's what that graph kind of looks like, and at t equals 2, that's over here. We're looking for the instantaneous rate of change. All right, so the slope of the curve at that point. All right, the slope of the curve at that point. So we're going to take the limit. And once again, I'm going to erase this and start over just to explain a little bit more. We're going to say, I'll use S prime of t would be the limit as t approaches 2 in this case, because we're doing it at 2, of S of t minus S of 2 all over t minus 2. So really the same setup as the last problem. We're specifically finding it at 2, so we're finding the derivative at this point. Now, eventually we'll maybe move away from this form and look at the one, and then we'll look at that in a few minutes here, but look at the derivative at a point which is right below that. Sometimes that's a little bit easier to, there's 2 other ones that might be, I don't know if I'll say they're easier, but they'll be more user-friendly in the future. But I want to start with this one first, because once again, this is just the slope formula. Slope between 2 points, and one of them we don't really know. We don't know this point. Okay, so we're trying to find it at a specific point, so that's why it's t equals 2. Or yes, so that's going to be the limit as t approaches 2 of 2 over t plus 1 minus 2 over what, 3, because if I evaluate this up here at 2, like 3, right?
2/3, wasn't it?
Yep. And then we get t minus 2. All right, so far so good?
Yep.
Now, once again, we're running into this problem. The easiest way to evaluate a limit would be to just plug this number in. Well, we can't, because we can't divide by 0. So we're going to have algebra, and we're going to have to do some algebra like we did in the other one. We did a little factoring. This might be different algebra, but we're going to have to do some algebra that'll allow us to eventually plug in that 2 for t. Right? This algebra is going to be a little bit different here. Right? Maybe it's not, but it's how we deal with things in how we've dealt with things before in algebra 2 and algebra 1. All right? Forget about the limit part for now. Let's just work with the expression here. This is what we call an improper fraction. We have fractions with fractions. So in order to simplify that, I'm going to multiply the top and the bottom by 3 times t plus
1. Okay.
Can you see why?
Yeah.
Because it's gonna get rid of those fractions there. Okay, it's gonna get rid of those fractions there. So if I do that, I'm gonna come over here, and once again, I'm not forgetting it's a limit. I'm just not gonna copy that down every time. Okay, if I multiply the yellow times this red, I would get what? 6.
Yep.
And if I multiply, oops, I hit something wrong here. If I multiply the yellow times this red, I would get 2 times t plus 1, right?
Yeah.
And then on the bottom, I'm just going to write it out like this. 3 times t minus 2 times t plus 1. Okay. So we're there. Okay.
Yep.
Well, now I'm going to come down here and I'm going to just kind of work with that and simplify it. I'm going to do some algebra. One word of advice is I'm not going to multiply this out because eventually I want to cross this off. So I'm not going to multiply that out. Okay, so maybe up here I'll do some work. This would be 6 minus 2t minus 2, wouldn't it?
Yep.
Okay. Well, that means that turns out to be what? Negative 2t plus 4. And then we have that over 3 times, oops, I'm running out of room here. So I'm going to go to the next page here. I'm going to make sure I take a look at what I have here. We have negative 2t plus 4 over 3 times t minus 2 times t plus 1. I think that's what we have.
Where did the negative? Oh wait, never mind.
I can go back. You know where it came
No.
from?
Yeah, I didn't know where the +4 came from, but I got it.
6 minus 2, right?
Yep.
Right. Well, I'm going to bring back this limit idea, or I'll come down here. Limit as t approaches 2. Once again, I should have brought it with every expression. I just don't want to. I'm saving space. Well, up here, I think I can factor out a negative 2. And look at that. Look what I end up with. Do I get what I want?
Yep.
Yeah, because now I can say
Donut.
boom, boom, and boom. Are we getting donuts or what?
I'm just kidding, Buff. He's working in the library with me. This is Sarah. I'm just teasing you.
That's fine. I'm joking around. I already had breakfast. Thank you.
Okay.
So we end up with the limit as t approaches 2 of negative 2 over 3 times t plus 1. Well, now we can just plug that 2 in and see what we get. And if we plug it in, I think we'll get negative 2 over 9.
If we plug in 2. Oh,
2.
Yep.
Yeah, because that's our goal, is to do all the algebra required to eventually
Yep.
plug that. All right.
Yeah, I was thinking it was 2/6.
Oh, but you got to multiply, right?
Yep, you're right.
Yep. Okay. So that's using that formula for a derivative at a point. Okay. Now, I'm going to go to another page here. Now, what's maybe more useful is the formula that, or the definition of a derivative on page 741. Now, I'm going to talk to you about why I think that's more valuable. And good thing you're on here, because this is benefiting everybody that didn't get up in time to do this. So you take one for the team, but it's all right.
Always
So-
do.
You always do. That's true. And you have donuts, so that's good.
Right?
All right. So I'm going to jump to another question here. I'm going to go to, let's see here. I want to look for a specific one here. I'm looking at the ones you guys were assigned because I want to do those. Let's look at number 30. That was assigned. Okay. It says to find the derivative if it exists. Now I'm going to show you why this is more user friendly, because it's maybe not, but it will be down the road. Okay. It says f prime of x is the limit as x approaches h of f of x plus h minus f of x. Excuse me, is that right? I might need to say f of h. Nope, that's right, f of x all over h. Okay, now that looks a little bit different than our slope formula, but I'm going to talk a little bit about why it's different. If it was our slope formula, it would look like this. Whoops. Let me erase here. It would be the slope between those 2 points. X, f of x, and x plus h, f of x plus h. But this is really what it would look like, wouldn't it? Can you see why it simplifies to just h on the bottom? Okay, so sometimes people think this is way different than the slope formula, but it's not. It's the slope formula. Okay, it is the slope formula. All right, so I just wanted to let you know that it's not like we're doing something different, it's still slope. So basically we're finding the slope between 2 points that are going to become the same point. So for example, oops, I got my, if this is my curve, I'm just making up a curve here. We can estimate the slope of a curve by finding the slope between 2 points, and then those 2 points can get closer and closer together. And as we do that, we'll get a more accurate picture of the slope at the specific point. Does that make sense?
Yep.
So those 2 points, it's like finding the slope between 2 points that are coming together to become 1 point. All right, so let's use that in question number 30. Let's go with this one. And then I'll show you why I think it's fairly useful. F of x is 2 minus 3x squared. Now, in the previous problems, we've been finding the derivative, or the derivative represents the slope of the curve at that point, the tangent slope at that point, the instantaneous rate of change. It means all those things really mean the same thing. But we've been finding it at a specific point. Well, instead, for this one, we're going to find it for every point. We're going to find an expression that'll give us the derivative, or the slope of the curve, at any point on this curve. Do you see why that might be more useful?
Yeah.
So I wouldn't have to do that formula if I wanted to find it at, for example, back here, when I found this at 2, if I wanted to find it at 4, I'd have to do all this stuff again.
Mm-hmm.
And instead of having 2 in there, I'd put in 4. So it might be more useful to find a rule that'll help us find the derivative of a function at any point. So here we go. We're going to use this guy up here. So it's the limit as x approaches h of f of x plus h minus f of x over h. All right, am I doing it? Did I write something? Hold on here. I might have to revise my, I have to revise my rule here. Sorry. I'm getting, this is not right. Okay. So I got to erase this too. I didn't look at, it's supposed to be, and it's still the same principle. It's a limit as h approaches 0, which if h approaches 0, these two points are becoming the same point anyway. Okay, so back up, my mistake. So sorry about that. I'm not trying to confuse you. All right. There are other forms where we do use it that way, but that's not the one that's on page 741. So obviously we can't plug in 0 for h right now. Same problem we had earlier.
Yep.
So we're gonna have to do some work. We're gonna have to do some work with that. So we're gonna say, and once again, just for, I don't want to write that down every time. It's still there, but I'll bring it back. But f of x plus h for this function would be 2 times, would be 2 minus 3 times x plus h squared minus f of x all over h. Okay. Now, once again, we want to get to the point where I can plug in 0 for h, so that's going to be some algebra. Well, let's do some algebra here. 2 minus 3 times x squared plus 2xh plus h squared minus 2x squared, that's not right, 2 plus 3x squared over h. Can you see what I did there?
Yep. Just factored that.
Just multiplied that out, yeah. And then I distributed the subtraction through this group here. Okay. Well, I got to go to the next page here. Make sure I can always go back if I need to. But then we're going to have, I'm going to bring this back. Limit as h approaches 0 of 2 minus 3x squared. All right, I got to go back. I forgot already. Let's see here. Plus 6xh plus 3h squared. Or minus 6xh minus 3h squared. It's because it was a negative 3 out front, right?
Yeah.
Minus 2 plus 3x squared, and all of that over h. So all I'm doing is a bunch of algebra. Okay, all we're doing is a bunch of algebra. I mean, until we get to the point where we call it a derivative and we evaluate the limit. Well, what happens now? Good things. Opposites. Opposites. And we're left with, we're just left with what's not crossed off.
Yep.
Now, we still have that problem with we can't plug in 0 for h, but, aha, look at some algebra here. The limit as h approaches 0. Each of these has an h, so I could factor that out. And now I can do this. Okay. So now I have to figure out what would be the limit of this expression as h approaches 0. Well, we did all this algebra so that I could plug in 0 for h. If I plug in 0 for h, I get that.
Okay, that's where I was getting confused because I'm like, I couldn't figure out how to get rid of the h's.
Yep. In some way, shape, or form, they're going to have to cancel out like what we've done here. Okay. They're going to have to cancel out kind of like what we did there. All right. So that's using what's called the definition of the derivative. Now, if I wanted, and once again, remember, this is f of x, f prime of x, if f of x is 2 minus 3x squared. So if I wanted to find the derivative at 10, it would be negative 60. If I wanted to find the derivative at negative 2, it'd be 12. So you see, I can use this to find the derivative at any point of this curve very easily.
Yeah.
You see why that's more helpful?
Mm-hmm.
Yeah, but we had to kind of have to build to get there. Okay, we kind of have to build to get there. Okay. Is this making a little more sense then?
Yeah, a lot more.
Yeah. And this is difficult stuff to do on your own. I mean, I totally understand that. All right, let's look at another one here. Let's look at number 32. That looks like a good one. All right, just another type. It's kind of like number 4, but we're going to do it in terms of the derivative. So this is number 32. F of x is 1 over x minus 2. Do you see that that's kind of like number 4?
Yep.
Because it's a rational function, okay? So we want to find f prime of x, which will be the limit, oops, as h approaches 0 of f of x plus h minus f of x over h. Now this looks the same, you know, this is just that definition right here. How we apply it to different functions is where it changes. Okay, it's going to be a little bit different algebra for different functions. Okay, so remember, once again, I'm going to say this again. I'm not going to copy this down every time. It's going to come back, but f of x plus h would be 1 over x plus h minus 2. F of x would be 1 over x minus 2. And then we have h. All right, so f of x plus h, f of x.
Yep.
Well, now we have that improper fraction thing again, right? Which we're going to have to deal with this algebraically, just like we did numbers 4, but it's maybe a little more abstract because there's more variables, okay? Sometimes it's easier to evaluate numerical, but this is where we're headed anyway. So if we can do these, we can go back in numerical and do them easily. Is what I think. So I'm going to multiply the top and the bottom by x plus h minus 2 times x minus 2. Does that make sense why I chose that?
Yep.
Because that's the denominator. So if I take the green times this, I'm left with x minus 2. And if I take the green times this, I'm left with subtract x plus h minus 2. And down in the bottom, keep in mind, I'm not going to multiply this all out because I don't need to. Things will work themselves out. Okay. All right, so this comes from multiplying these two. And this comes from multiplying these two. All right, so far so good?
Yep.
Now, let's just look at the top. I'm not going to mess with the denominator yet. We'll do that later. The top, isn't there a lot of, I mean, if we're subtracting here, I see x minus x. I see -2 minus a -2.
Yeah.
Looks like the top is just going to be -h, isn't it?
Yep.
I'm going to put a little wall there. Okay. So let's remember that. I'm going to go to the next page because I don't have any more room here. So because of just algebra here, the top turns out to be h, which is encouraging because then I can cross that off with this guy, right?
Yep. Then you're with
Okay.
-1 on top.
What's that?
Then you have -1 on top.
Yeah. Yes.
Okay.
But I'm going to bring it all back over here because I'll explain some more. It was x plus h minus 2. And then it was x minus 2. And yes, exactly. We're going to cross this off and cross this off. So we have the limit as h approaches 0 of -1 over x plus h minus 2. Oops, that's not very good. 2. X minus 2, which if we let h be 0, that's what we have. Uh-oh. R2D2.
R2D2. It's my text ring.
Yeah, I figured it was something like that.
Yeah.
Hey, Derek, you know how old I am?
Nope.
I student taught when Mrs. Learwood was in high school.
Yes.
Oh.
Under one of the best teachers ever, right? Mr. Stites was amazing.
Yeah, he was my favorite teacher.
Yeah.
Part of the reason I went into becoming a math teacher.
Yep.
So this would be that derivative that we came up with. That is the derivative of 1 over x minus 2.
Awesome.
Yeah, so hopefully this is helping and making more sense. And whenever we get done, and I'm not in a hurry to be done or anything, but I'll share this stuff with everybody else. Okay. Now there's one other type of function I think I want to look at. It's number 6, and it gives you a hint there, but it's a different kind of algebra. Okay. Polynomials. If we're finding the derivative of polynomials, we're going to do a lot of this. Plug it in, multiply things out, things will cancel out really nice and neat. Okay.
Yep.
If they're rational functions, excuse me, let me go back here. If they're rational functions, we're going to have to do a lot of this work. Get rid of the improper fraction idea and make that work. Okay. But if they're like number 6, it's a radical, and that's a little different. S of t is the square root of t plus 1. We want to find that at t equals 1. Now I'm gonna do this one using that formula that we just talked about, the definition of the derivative. And the hint is what's really important, but sometimes it's a little tricky. And I like to go through each of these 3 types with students. Okay, so once you find the derivative for the function, finding the tangent slope is easy. We'll just plug it in, and we'll do that in the end here. So in our case, s prime of t would be the limit as h approaches 0. And I'm going to just use the same variable, s of t plus h minus s of t over h. So it's the same formula. I'm just applying it to, instead of f of x, s of t. So that shouldn't be confusing. All right. It's just we're just having a different variable, different function name. So that's going to be, once again, I'll say it again. I'm not going to write this down every time, but we'd have the square root of t plus h plus 1. Right, that's this, minus the square root of t plus 1. Okay, and that's this, over h. All right, so it's just applying the rule to a different function. Getting it started like this should be the same no matter what type of function it is. Now, they give us a hint there. They say rationalize the numerator. Okay, rationalize the numerator. And that's not something that we normally do. That's why we're looking at this one together here. Well, in order to rationalize the numerator, I got to take the top and the bottom times this. T plus h plus 1 plus the square root of t plus 1. And I got to do that on the bottom too. And I'll explain why that's what we have to do here when I'm done writing this down here. Now, the reason we have to do that is kind of like when we talked about complex conjugates back when we talked about complex numbers. All right, eventually, or just shortly here, we're going to do FOIL right here. And it looks like the outside and the inside are going to eliminate themselves. And what that's going to allow us to do is get rid of all the radicals in the numerator. Okay, you maybe can't see that yet, but that's what it's going to do. Okay. So we're going to do that FOIL. I'm going to do that in green here. First, well, that would just get rid of the radicals, and we'd have t plus h plus 1. Now look at my outside. Outside would be multiplying those two. Okay, and then look at the inside at the same time. What would be true about the outside and the inside?
I don't know. I kind of got lost.
Okay, where did you get lost?
Okay, so you multiplied the first ones, and then where were we at?
Now I
First
went
and last?
outside. Nope, I just went first. This is first right here.
Yep.
This times this is t plus h
Yep.
plus 1.
Yep.
Now, the outside and the inside, aren't they going to be exact opposites of each other?
Yep.
So they're going to be eliminated. Okay.
Yeah.
I'll say the outside would be the square root of t plus h plus 1 times the
Okay.
square root of t plus 1.
Yeah,
and the
then
inside
deduct the each.
is going to be the opposite of that. So they're going to be gone. It's
Yeah.
kind of like a difference of squares.
Yeah.
So that's why we did that. That's why this is rationalized the numerator works. Okay. And now we're going to do our last. Well, that's going to be the opposite of t plus 1. If I multiply these two. I know I got a lot of arrows and it gets confusing, but I'm trying to talk my way through it too. All right. And once again, that's all over h. Okay.
Times that other stuff. Or no?
Yes. I forgot about that. You were correct. Times all that other stuff. And once again, we're not going to multiply that out. But let's just look in the numerator. The numerator is going to simplify to what?
H.
Just h, okay? So I'm going to go to another screen. And we're going to have h over h times the square root of t plus h plus 1 plus the square root of t plus 1. That's a good thing, right? H's cancel again. Right, we're able to cancel those h's as we had before. So we've taken care of the problem with our limit. So now we have the limit as h approaches 0 of 1 over the square root of t plus h plus 1 plus the square root of t plus 1. And what happens is if h gets to be 0, these two are the same.
Yep.
So that means s prime of t would be 1 over 2 of those radicals.
Let's see.
Make sense?
Oh, yep. Okay, yeah.
Because I'd have this plus this. I'd have,
Because H is 0 then.
yep, as h approaches 0, exactly.
I have gotten sick once from 0.
So now, question 6 actually asked us, if we go back there, it asked us to find the what?
Instantaneous velocity.
Velocity at t equals 1. So that means we really got to find s prime of 1. And that would look like this. All I did was I plugged in what?
Yep.
Plugged in 1 for t.
So you're lucky you haven't gotten sick.
Okay. So those are kind of the three different types of functions we'll deal with. The thing you want to remember is when it says instantaneous velocity, when it says slope of the tangent line, when it says derivative, those all mean the same thing. They all
Okay.
mean instantaneous rate of change. I mean, all those things mean I got to find the derivative at a point, or find the derivative, I mean, whichever. Okay.
Can we do one of like 7 or 8?
Yes. All right. Use the graph to estimate the slope of the tangent line. Now you're just estimating there, right?
Yeah. Because I got like something different totally than the answer key got.
What did you get for 7?
Let's see. I think I copied it eventually, so I got 1.
Okay. What did you initially get then?
I don't even remember.
All right. So this is just an estimate, so it's not perfect. So, I mean, this is what this curve kind of looks like. This is number 7, right? So the curve kind of looks like this, right? So if we're trying to estimate the slope of the tangent, we're trying to figure out what's the slope of this line that just touches
Yep.
at 0. Well, we know it's positive something, right? So they just said it looks like it's positive 1. If you said it was positive 2, you're not wrong. It's just an estimate. Does that make sense?
Okay, that's all you gotta do then.
Yeah, it's an estimate. Okay.
Okay.
Now let's look at number 8. We can look at all of them. Let me go. They don't take a lot of time. Not time is an issue.
So if I said like 8 would be 2, that'd be okay.
No.
Dang it.
Sorry. And I'm going to show you why. Just give me a second here. So that curve looks like a cubic function. And once again, my graph isn't perfect. So we're trying to find the slope of the curve at 1 though now, right?
Yep. It's gotta be negative.
So it's got to be a negative. Yeah. So if you said -1 or -2, that'd be good. So the problem you said 1, it should be a negative number.
Okay.
It should be, okay, because it's going downward. It's going downward. Now for number 9, what did you say about number 9?
There isn't one.
There isn't one because it's what we call a corner. Same thing with number 10. There wouldn't be one because it's not continuous there. Okay, so these are just estimating.
Yep.
Okay, these are just estimating. If, like, for example, if we estimated this number 7, if we estimated it at, let's say, 2, it would have to be steeper, right?
Yeah.
But they told us at 0. Now, if we actually knew what the function rule was, we could use that definition to find it exactly. But we don't. We don't have that. Okay? Feeling better about this?
Yeah. And then okay, just one more. Can we do 11 or 12?
Yep. 11, graph the function in a square viewing window and without doing any calculations, estimate the derivative. So it's a lot like 7 and 8. So give me a second here. I'm going to go to my calculator. All right. I think I have my calculator here somewhere. All right, so here it is. So we have, you just want to do number 11?
Sure.
X squared minus 2x plus 5. And we want to estimate the derivative at 3. Or does that say derivative?
Yep.
Yeah, estimate the derivative of the function at 3. Okay. So, okay, I said 3, I meant 5 here, but we're going to estimate at 5. So zoom, I'm going to go zoom 6. At 3, and I'm just going to do this. Let's see, I can do this and calculate the value at 3. It'll just put a little cursor on there. Okay. So if you want to estimate that, it's a positive slope, right?
Yep.
Let's see. We just have to, I mean, it's an estimate. The exact value is 4, but you should estimate something, 3, 4, 5, 2, 3, 4, 5. You don't know exactly what it is.
Yeah. So
It's just an estimate.
so it wouldn't be 8.
8, I think. Okay, so let's try it. Okay, so we know
That's what I kept doing. I got like 8.
the y value is 8. That's the y value at that point. Okay,
Yeah.
that's not the slope. That is not the slope.
Oh.
Okay, so let's just test. Like I said, the actual value is 4. And I know that because I've taught this class a long time. So, but well, I'm just saying 4 times x minus 3. Am I just using point slope form here?
Yep.
All right. Does that look like it just touches there?
Yeah.
Yeah. My window isn't really that great, I guess. Let's go 0. Let's go to 20. All right. Once again, I know that would have, but if you were to guess 8, I think you'd see that's probably too steep.
Yeah.
So remember, we're not talking about estimating the y value. We're estimating the slope of that curve at that point.
Mm-hmm.
All right. All right. Does that help?
Yeah.
All right. Anything else?
I think that's all I need.
Okay. Well, glad to help. Glad I had participation. Now everybody will benefit from you. Because if no one's here, I don't do anything. All right.